The following demonstration illustrates the basic operation of a Vickers variable displacement inline pump used on today's commercial aircraft. Normal response time of the pump is in milliseconds. Therefore, the pump action was slowed down for this demonstration. The inline pump is mounted on the aircraft's engine to provide hydraulic power for operating the aircraft's flight controls. As the aircraft's engine rotates, the pump drive shaft, cylinder block, and pistons rotate to produce a pumping action. This pumping action is generated by piston shoes, which are restrained and slide on the shoe bearing plate in the yoke assembly. Because the yoke is at an angle to the drive shaft, the rotary motion of the shaft is converted to piston reciprocating motion. As the drive shaft continues to turn the cylinder block, the piston shoe continues following the yoke bearing surface. This begins to return the piston into its bore toward the valve block. The fluid contained in the bore is pre-compressed, then expelled through the valve block outlet port. With each revolution of the drive shaft and cylinder block, each piston goes through the pumping cycle, completing one intake and one discharge stroke. High pressure fluid is ported past the blocking valve to the pump outlet. The blocking valve is designed to open and remain open during normal pump operation. Internal leakage keeps the pump housing filled with fluid for lubrication of rotating parts and cooling. The leakage is returned to the system through a case drain port. The case relief valve protects the pump against excessive case pressure, relieving it to the pump inlet. At pump outlet pressures below 3,000 psi, the yoke angle is held at its maximum angle. The pressure compensator is a spool valve that is held in the closed position by an adjustable spring load. When pump outlet pressure, system pressure, exceeds the pressure setting, 3,000 psi, the spool moves to admit fluid from the pump outlet into the actuator piston. Decreasing system flow demand causes outlet pressure to become high enough to crack the compensator valve open and admit fluid to the actuator piston. This control pressure overcomes the yoke return spring force and strokes the pump yoke to a reduced angle. The reduced angle of the yoke results in a shorter stroke for pistons and reduced displacement. Fluid pressure continues to build until the blocking valve opens. Flow from the pump is maximum until the system is full, and opposition to the flow builds, which causes the fluid pressure to increase until the pump starts compensating, and this goes into cutoff operation. During cutoff operation, fluid pressure builds and is ported to the compensator spool, which moves and allows fluid pressure to be metered to the actuator piston, which de-strokes the pump. The compensator starts moving at 2,850 psi and will completely de-stroke the unit at 3,000 psi. The pump remains in cutoff mode until the system demand changes and then goes back into full flow operation for cycle completion. During engine startup, the flight crew energizes the pump solenoid valve from the cabin. When the solenoid valve is energized, the outlet fluid is ported to the EDV control piston on the end of the compensator. The high pressure fluid pushes the compensator spool beyond its normal metering position. This removes the compensator from the circuit and connects the actuator piston directly to the pump outlet. Outlet fluid is also ported to the blocking valve spring chamber. This equalizes pressure on both sides of the blocking valve, causing it to close due to the force of the blocking valve spring. This isolates the pump from the external hydraulic system. The pump strokes itself to zero delivery at an outlet pressure that is equal to the pressure required of the actuator piston to reduce the yoke angle to nearly zero. This depressurization and blocking feature can be used to reduce the load on the engine during startup, and in a multiple pump system to isolate one pump for checkout purposes.